And we have Yidi.
So thanks. So finally, after all those lectures, we're going to conclude the topic of Calabi-Yau matrix by actually computing the Calabi-Yau matrix. So this tutorial will consist of 3 parts. So part 1, I will give you a really simple for example, and we're going to have some fun and read everything from scratch. Of course, this code model will have many flaws. It's going to be wrong in many different ways. That's why we'll introduce the other 3 packages. And then you can do some like real calculation and play with those packages. All right. So first, let me quickly remind you the problem we're trying to solve. So suppose we have a set of points. Like they can be any points. Doesn't matter. Like it can be like a Calabi-Yau, it can be on a sphere. It can be like quite general. So now we feed the points to a neural network, and then you want the neural network to give you a matrix G, and then you train the network so that this G satisfies some constraint L. So we have LG equals 0. So this is quite the general setup. In our specific case, we want the points to be on this hypersurface, f equal to z1 to the power of 5, z2 to the 5, plus z3 to the 5, plus z4 5 to z plus z5 to the 0. So this is the points we want to sample on. And the condition we're going to use here in this, for example, is just the Ricci flatness. We have L is the Ricci flatness. So this is equivalent as the integration of 1 minus 1 kappa the omega kappa omega bar. So it basically means on this hypersurface, on every single point, that those 2 volume form should match up to a constant k. Right. Okay, so now let's break down this this problem into several steps. So in part 1, you can so you can first run those installation and then import packages, and there'll be some function we'll be using later, and you can just totally ignore those code for now. So the point at the beginning we need to generate points on the Calabi-Yau, right? But this generation can be pretty tedious, so we'll just give the points to you. We'll borrow this point generator from the CY matrix package. If you run this will give you a bunch of points. Let's first print them out and see what they like. And print out the first 10 points. So if you look at them closely, all of them are like 5-dimensional complex coordinates. And the last one is like z5 is always equal to 1, and then the other coordinates always have the they're always like smaller than the last one. So the reason is if you look at this hypersurface, recall on projected plane we have z1, z2 to z5 is equivalent to lambda z1 to z5, which means you can divide the whole thing by one of the coordinates. And for example, if you can divide the whole thing by z5, and now you can define z1 over z5 as a new z1. So your hypersurface will have like 4 coordinates, z1, z2, z3, z4, and the last one will be 1. Mathematically, you can do this for any coordinates, but numerically, you don't want your coordinates to be like something infinite because you want to feed this to a new network. So usually we will compute the norm of each coordinate, and we'll always divide this by the one with the largest norm. So here, like all of the points here are they all have the z5 as their maximum norm. So this is just a collection of points on the hypersurface. It does not cover the whole hypersurface. But to simplify the question, well, we just use those points. Okay. And now suppose we have the points. The next step is to compute this omega omega here. So basically, we want to compute this volume form and then this volume form. And this is something we know. This first, we're going to compute the holomorphic volume form, omega which omega bar. And to compute this, we first compute the free form. Omega. So this is defined as omega equal to 1 over partial f, partial d1, dz2, which dz3, which dz4. And now you can actually put any coordinates to be here. This is also equal to 1 over, can you see this? 1 over partial f, partial z2, then dz3, which dz4, which dz1. Maybe up to a next time. But, so basically, you can put any. You can put any coordinates to be here. But again, for a numerical reason, we don't want this number to be too small. We don't want to have like something 1 over a small number. And then we can compute the value for partial f partial z1 and partial f partial z2, and then basically compare which one is larger. Again, to simplify the question, we'll just use omega equal to 1 over partial f partial z1 here. So you'll see that this will cause some problem. But to simplify the calculation, we'll just let omega equal to this. So we have 1 over, in our case, because f is this hypersurface, so partial f partial z1 will just be 5 times z1 to the power of 4. Now, once we have the omega, we can take the conjugate and then compute the volume form as omega which omega bar. So now we have this term. So to compute this volume form omega here, we want to define the network first. So the next step, once we have this omega bar, we can define a new network to represent the matrix G. So because the coordinates here are all complex numbers, network in theory the network can deal with complex numbers, but then the training will be a little bit harder. So we will instead just use the real network, and then we just convert the coordinates to the real coordinates beforehand. So before this step, you first need to convert points to real coordinates. So instead of a 5-dimensional vector, we'll have like a 10-dimensional real vector. So the input dimension of the network should be equal to 10. And then again, the output dimension, because G is like 3x3 complex matrix, but it's also Hermitian, so we only need like 3x3, 3 times 3 equal to 9. Now we have the network and compute omega by omega, can get G and then compute omega from that. So next step, we'll define this loss function to represent this integral and define a find a loss function L. So the first step, again, because the output of the network are all real parameters, so we want to convert this to a vibratory Hermitian matrix. So we're going to use this function we defined beforehand. So this is called convert to Hermitian. So we can simply do something like the G equal to convert to Hermitian. G. So let's say you define your loss function to be taking G and taking the holomorphic volume form omega bar. Then you can compute, first to convert G to a complex matrix, and then you can compute omega. So omega will be convert G, and then your omega will just be determinant of G. And then you can represent this integral as the average. So equal to do numerical integration, you have like n over v over n times the basically the sum of 1 minus the ratio of 2 volume form. And also there should be like a kappa here, but for, to simplify the question, we'll just set kappa to be 1. So know that this notation is actually wrong, because if you recall the lecture on Wednesday, there will be like a mass function, right? If the integral, if the measure you choose for this integral is the same as the measure you use when you sum the points, then you can just like rewrite this integral as a summation. But because they're usually not the same, so in theory you will need to multiply this by a mass function. But again, that's like kind of hard to implement. So you can just like approximately using this this one as your loss function. Missing mass function here. And this one also does the job, because like ideally omega and omega wedge omega bar will be always equal to 1. So ideally, if this is 0, it doesn't matter if you multiply this by mass function or not. But if you want to control the error, you want to estimate like how large your error is, then you will need to implement this mass function. So basically, your loss function will consider those 3 steps. So first, you convert G to Hermitian, and then you compute the volume form omega, and then you can compute your loss, and then finally you return the loss. So now we have the loss function. We have omega, we have omega wedge omega bar. The next step will just be just like training the network so that this loss function equals 0. The next one is just string steps, and you can also do some like plotting. So that's pretty much all of the steps. So first we generate the points, and once we have the points, we compute the holomorphic volume form by omega to 1 over 5 times C1 to the 4. And then we define this network and define the loss function. Then you just like train the network, and when it's done, the G you get here will be a Ricci metric, ideally. Okay. So I will give you like 10 to 20 minutes to fill in the gaps, and then we can work on this together. So the two variables are the G, which is the output. So G, maybe I'll write this at NN output. So this will be like a pure numerical. Yes, you can use NumPy. You can use the TensorFlow. They have their own version of NumPy, basically. Everything will be numerical here. There's no symbolic calculation. And this holomorphic volume form should be computed. It's just this one, this omega wedge omega bar. So yeah. this is also numerical because like you see omega is 1 over 5 times z1 to the 4. So z1 is like, you know, z1 from the point. So z1 is just like the first coordinates of this linked list. And so you can compute this as a numerical value. And then just take conjugate, and then because we don't care about the basis, we just multiply this with the conjugate. The first step is basically you from this list of points, compute 1 over 5 times z1 to the power 4. I can give you a hint. So you can start from the omega here, right? So because we want 1 over 5 times z1 to the 4, and we can say omega is 1 over like 5 times because we want first coordinate, so this should be points 0 and 4. So you can print out the omega. So this will be a list of scatters. And then you just take the conjugate of this and then multiply omega by omega bar. Yeah. There's sums over all of the points. Yeah. Because is with, I mean, it can be within the loss function, or you can do it outside the loss function. It doesn't matter. The idea is like we want that integral. So that summation is basically this integral. Instead, we want to minimize this. We want to minimize this so that this can be equal to 0. So we just rewrite this integration by taking the average. So this is the integration over the whole manifold. That's why we integrate on
yeah, I think what I'm asking is, should I be thinking of G as array of metrics evaluating
yes.
different points?
Yes.
Or is one metric?
Like for different points, we have a different G.
Like literally in the context of this, am I thinking about it? And then output is associated with a set of points or one point?
It's like a set of points.
A set of points, right?
So if you have like 100 points, then your G will be like 100 by 3 by 3. That's it. No, this basically means, okay, so let me, yeah. That's right, that's basically means, no, this is a complex coordinates. So this is like, yeah, so for every point, I take the first coordinates of that point. So this is like 6.4 and then like 7.5, and you can see that it's like, yeah, it's like this one, this one, this one. you can compute like the holomorphic volume form from. You can feed this to the loss function. You can compute this beforehand, and then these are like the y value for the like supervised learning. So you compute these beforehand. You compute g which is the output of your network. Then you compare those two in your loss function. So basically, next step you should have something like omega bar is the conjugate of omega, and your homomorphic volume form is just omega times omega bar. If you print this out, those should be real scalars. Yeah. Yes. Those are like the real scalars. If you look at those values, like some of these are like 5 times e minus 2, and these are like 3 point e minus 1. Those are pretty fine. It's like less than 1. But there are some of those like really huge numbers, like 4.3 times E03. So this is because the one I mentioned here, because when this value is too small, your omega will probably blow up. And this will actually make your training much harder. Yeah, yes. Yeah, 2 more days. All right, so once we have the homomorphic volume form, we can define the network. Before that, we will need to convert the points to real coordinates. So we can find the real part of the points, and then find the imaginary part of the points, and just combine them together using TF concat. All these points real. So if we print this out, you will see that we have this, the point is convert from complex coordinates to 10 real coordinates. And then we can define the network. To do this, you can open ChatGPT and say, write me a network in TensorFlow with input dimension equal to 10 and output dimension equal to 9, please. Okay. It works pretty well. So we just need the modal part. All right. Coding is easy, right? Just call this CN metric. The TF keras. Right. So the input dimension will set this to 10, and then output dimension will set this to 9. So this has like one hidden layer. So the first layer is like 10 times 64, and then 64 times 32, 32 times 9. Yeah. So now we have the network. We can continue to define the loss function. So again, first. Think about this. Yeah, maybe just that's right, because we wouldn't want this to be normalized. Yeah, we can just remove this. Thanks. So we continue to define the loss function. So because since we already have G as a Hermitian matrix, we can compute omega using the TF linear algebra DET D. So that's the volume form here, and the loss function will be the sum of the whole thing. So we can just assume V and kappa equal 1 for simplification reasons, and this is just TF. The average is called TF reduced mean, 1 minus the ratio of omega and the homomorphic volume form. Okay, so then we can just write the training steps. So we define the epoch equal to 0, and the maximum epoch be like 300. And so, well, epoch less than maximum epoch. Can use this gradient tape to track the gradient. So the loss function is defined as a loss function. So the input of this is the output of the network. So this is an metric which takes points real as input, and also the homomorphic volume form we just computed. And the gradients of this loss function with respect to the trainable weights of the network is escape gradient loss and n metric trainable weights. And then we can define optimizer. Optimizer is TF keras. Optimizers, we use the atom. And we can then apply the gradient. This is like the gradient descent procedure. And we can also define, let's just define the loss history to track the loss during the training. So we can append each loss to this list. And we can also print for every 10 epochs, we can print out the loss. And then we do epoch equal to plus 1. Yeah.
The homomorphic volume form to flow
Shouldn't matter. Yeah. Yeah, this omega. Wait, there's one more. It should be EFFs. Then everything should be real. Okay, so we need this this part. We might nice start training. You can see the loss start go down from 1.2 to 0.5, something like that. Yeah. And if you plot the loss function, the loss history, you should see so it's going down. So initially, this value is like 1.2. Ideally, we want this to be 0. But again, you can there's some limitation because of this. If some of this number is too large, then it becomes really hard to train. But generally, you can see this trend is like slowly going down. You can also like just print out some of the G's and see how those matrix look like. You can do points real and then convert this to Hermitian. Let's just pick the first 3 values. So those are like 3 by 3 matrix, and they're all Hermitian. So ideally, this will be the Ricci flat matrix we want. And here, like the loss is still like pretty large, but this is like one of the best approximation we can get from this setup. So of course, this way model has a lot of issues. For example, this is non-Kähler. So we didn't put any restriction on G. So there's no G can be anything, can be any 3 by 3 matrix. And also, this is only on one patch, and it's not globally defined. So if you transform your points from one patch to the other patch, then the G will not transform accordingly. So the transformation will be wrong. And also, there's a lot of like numerical issues like this. And the list just goes on. Okay. So to solve those issues, like one way you can do is, for example, you want to add a Kähler restriction to this. Then you also have like something similar like this. You have like some sort of function like of G, it's equal to 0. And we can basically define something like a Kähler loss, which takes G as input, and there will be your Kähler condition here, and then you return your loss function, and then for also have something like transition loss. So you can compute like when you transform the points from one patch to the other, like what's the difference of your matrix G. And we can put any sort of condition like this, and then write this as a loss function. And at the end, you can do like the total loss will be equal to like Ricci loss plus Kähler loss plus Kähler loss plus transition loss. So for each of these conditions, you can have like one loss function. And you can also put some weights on it. Let's say if you want to you want to make sure your network is like as Kähler as possible, you just like you can multiply this term by 5, and also you can multiply the other terms by 0.2 or something. Right. And this will help you resolve those kind of issues. In the spherimetric package, every loss function is defined already, so you can. I'll show you later. For now, I can give you another like 10 to 20 minutes just to make sure you understand what's going on here. So we start from the points generated on Calabi-Yau, and we compute the holomorphic volume form omega with omega bar, and we define a network which takes the points as input and then generate the matrix G as output, and then we define the loss function which gives you this constraint of the Ricci flatness, and then just train the network, and you have this kind of loss curve. If you refresh the page, you can probably see the updates. All right, so that was the basic idea of how you solve this problem. So the spherimetric and also the other packages basically follow the same kind of idea. So first we import some of those functions, and first we define, after we import the functions, we define points generated. So in spherimetric, the hypersurface is represented by this tensor. And print this out. So this basically represents the hypersurface we wrote down here. So the row basically means how many terms you have, and then the column is like the coordinates. So the value here is the index. So like the first, this basically means like z1 to the power 5, and the second one is like z2 to the power 5, and then so on and so on. And if you want to have something like z instead of z1 to the power 5, you want to have something like z1 to the 4, and then z times z2, or like z1 to the 3 times z2 times z3. You should have something. This should look like something like this. So the first row should be let's say 4 1 0 0 0, and then the second row can be like 0 3 2 0 0. So this means z1 to the power 4 times z2 plus z2 to the power 3 times z3 to the power of 2, and you can have like as many terms as you want. So once we define this generator, we can generate some points. As you have seen in the lecture this morning, we have this prepared data set and prepared basis. So the basis is like, recall here we want this want to compute which one has the largest partial f partial z. So you will need some information about the derivative and everything. So the basis is just contain those kind of information, and then you can define some callbacks. So they are like the functions that can track your different measures after each training step, and the network is basically the same as we just seen. So you have like number of layers and then number of neurons each layer, and you can change the activation function change the maximum epochs, and then the batch size, because like you can have as many points as you want, but usually you cannot fit too many in your GPU. So you can choose a mini batch. And then, as I just showed, you can change the weights on your different loss functions. And then you can define our model. There are like different options. You can check those on the GitHub page. Here we'll use this multi-FS model. So this is GFS times 1 plus GNN. So GNN is a network, the metric represented by the network. And then the loss function, you can define loss function here. So everything is written for you already. So sigma loss is the one we just done, and then we can also do like color loss, like transition loss, and then like volume loss, and then you just train your model. This will take a little bit longer, but once it's done, you can do some plotting. It should look like similar to the one we just did. So you can experiment with different hyperparameters. You can change which hypersurface you want to sample points on. You can also change some models, and also you can play with different loss functions. The other package is like CBAJAX and ML geometry. And as you have seen in the lecture this morning, you basically choose different like there are different ways to construct the matrix. Some of them use like scalar potential, and some of these just use the just directly represent the elements of a G. You can check those. I think all of these packages have like well-written notebook in their GitHub repo, so you can just feel free to check them. So we have like 30 minutes left. You can play with the CY metric data, CY metric package, and you can try to train the network and tune with some of the parameters. So it takes some time, but you can already see the total loss and the value for each different loss function. So essentially you want everything to be 0, but the scalar loss and the transition loss, probably care more about those. And the volume loss is just 0 because we just set compute cover beforehand. So the volume should always be a constant. Like all volume should always be a constant, and then ratio loss should be 0 because if we already defined this is basically the same as the sigma loss. So you can see the total loss is going down from 1.4 to 0.1 something. So if you finish your training, you should have like 4 plots like this. I think I might be something wrong like somewhere. But like if you're training ideally this transition loss should also goes down. But like if you see like a different pattern, then you can like try to tune some of the hyperparameters. Or sometimes you can see like sometimes the transition loss just goes up and then goes down because like the loss function is a summation of all of the possible losses. So you may do some weird thing. So I will upload the complete version afterwards. So that's pretty much all of the tutorial supplements. If you have any questions, you can also send me emails. Do you want to?
Okay, everyone. So this brings us to the end of the school. Thank you, Yidi, and many thanks to all the lecturers and the tutors. I think the success of this school relies on their hard work. Most of the material is already up on the school page. The slides are there and the notebooks, and we'll collect more if there is anything that needs to be added. The recordings will be put on YouTube. At some point, there will be a link in the following weeks on the school page to the YouTube site where you can watch the recordings. Thank you all for coming. I hope you enjoyed this week. I hope you enjoyed being in Oxford, and I'm sure you learned a lot. I learned a lot in this school. So have a safe trip back home, and I'm sure we'll see each other again somewhere at some point. Thank you.